Okay, let's go ahead and code up a hash table with open addressing. So we look at this code from last time. It was hash tables using not open addressing, but chaining with a linked list. Good. So we're going to copy this code over. I'm going to close this file. CP hash table over to hash table open addressing.cpp. Then we'll go ahead and gvim that thing. Gvim that thing. We'll open it up in gvim.
We're just having an interesting day today.
All right. Well, we have a node. That's good. Key value. But now we don't have a list. We just have a hash table of hash nodes. Anything else? Is that about it? That sounds.
Wait. Do you want to say hash node?
I sure do.
Sorry. It has node.
It had node.
It has node.
Sorry if I offended anyone online.
Sorry.
All right.
Continue, I'm sorry.
And we're doing terribly. All right, we're going to comment this out because this was the extended test.
We're just having
This is a great day, guys. All right.
I think we're all just so tired and done.
So our so we want to be able to insert some things. Let's try and insert, I don't know, 10 with, who's going to be 10? Paul? Sure, good old Paul.
Good old Paul.
Good old Paul. Actually, let's just run it right now and see what happens.
Wizard of the West?
Wizard of the West. You think it's going to compile? No.
No.
Yeah.
Of course not.
Good.
What is it?
All right, so we need to fix insert. How do you insert it to this thing? Well, we get our node. Really, we're just doing up position equals the node, right? Yeah.
Yeah. We have to add some stuff, like if it is already filled.
Yeah. Need to fix if there is a collision, so we'll ignore that for now. How do we search? We get the position, and do we need to iterate through things? No. Yeah, that's just silly. It's just silly. So we'll just return m hash table sub position. Wow, this looks easier. How can this possibly be harder?
It looks easier. That means it's harder.
I keep wanting to write the hast table. Is it m value? Is that what I called it? Good. Excellent. So I can put Paul in. Who else are we putting in?
Steve.
All those guys.
Gertrude.
Ada.
Gertrude works.
How do you spell Guter? How do you spell that name?
Oh.
Gertrude.
Gertrude. A computer science major in that English.
Yeah, Gertrude.
Wayne.
No, we're doing girls' names only.
Oh, I'm sorry.
Now we can do Wayne. I like Wayne. That's what I do. What about Phyllis?
Phil.
Did I spell Phyllis?
No.
I thought you just put Phil's like.
P-H-Y-L-L-I-S, right? Phyllis. Or
No, I think it's
No, it's not.
Phillys.
Physics.
All right, this is how I spell Phyllis.
I'm sure somebody out there has that name spelled like that.
I will search for 10, and what should we get?
Paul.
Good. And if we search for 16, we should get.
Phyllis.
All right.
Where? Why?
Well, well, because right now the keys make sense. We're only inserting them into the correct location, And then we're not. Do we have any collisions?
No.
We don't have any
That's
collisions.
fine. That's why it doesn't.
We don't have any collisions. So let's add some collisions.
Yay.
I don't even know if that's how you spell Suzanne.
Probably not.
Thanks.
It doesn't look great.
It looks fine.
Oh wait, this is the same key. What's our mod here? Our mod is the size. All right, let's knock this size down a little to 100. So now we just need to add 100 to things if we wanted to collide. So there, Suzanne should collide with Steve.
That one's on you.
I walked right up to that one. All right, so if I do a search on 11, what should I get?
Error.
I should get Steve.
Yeah, 'cause Steve's first.
But I have Suzanne. Well, that's because the key of 11 goes to Steve. So if I have a key of 11, I should get Steve. But if I ask for 111, I should get Suzanne. Right? So should be Suzanne, not Steve. But instead, it's I said that backwards.
Yeah,
Should be Steve,
Not Suzanne.
not Suzanne, but Suzanne collided with Steve and caused issues. There we go. All right, so how do we fix it? Fix it, fix it, fix it.
If there's something already in that spot.
All right, so Boolean, wait, skipping ahead. How do we know if something's in that spot?
A Boolean.
Why would we need a Boolean?
To see if it, like,
If
because if
there's
it's
something
full,
that-
then it needs to return true.
Or if like if
Yeah,
the
so it pretty much
location
does
is
not know.
filled.
If it's filled. Okay.
So it's not.
So bool, we'll say m filled. I'll leave it like that. Okay. Now, fortunately, m filled. Well, we need to initialize all these keys to the right size. So let's go do that real fast. For int 0 I is less than size I plus plus. You okay there?
Yep.
I dot m filled equals false. All right. That way we know none of the things are filled up, right?
Yeah.
Totally. Good. Making sure it's still compiled. All right. So after we insert something, we need to also make sure position dot m filled equals true, right? Mm-hmm. All right.
Looking good.
Looking good. So now what happens? We need to fix if there's a collision. So how do we know if there's a collision?
If it's true.
If M filled.
Hash table sub position dot m filled.
Equals true.
Well, no, this is equal false.
Oh, yeah.
Right? Because if you're doing it initially.
Sure. Well, if it is filled, what do we need to do?
Stuff.
Yeah, stop. Don't you have to, like, put it, like, to the next free one?
Yes. So how do we do that?
Oh, it's just the key
Go
plus
through
one.
until.
What?
The key plus one?
So position
Yeah.
plus plus. All right, but hold on. Can't that be filled up?
It
Yeah.
can be, so.
So do a quadratic.
So while. Ah.
That's a good idea.
We also need to make sure that if it's not quite correct. Position is greater than or equal to size.
Yep.
Position mod equals size.
Ooh.
That way it wraps around.
Okay.
Do y'all see what I just did there?
Yeah. Good.
Is anyone confused about what I just did there? No? Okay, great.
No. Okay. Good.
Find
That's
and
what Suzanne's-
open position. Huh?
That's what Suzanne's doing? Wrapping
Yeah.
around?
Yeah, she's gonna wrap around.
Oh.
That's not.
Good job, Dan. Good job.
No,
We're just walking.
That is not at all what I
no, that's definitely what you said.
Dang it, it's payback.
It is.
This is what happens when you make us choose buildings. You just-
All right. So now if we run it, let's see what happens. Uh-oh. I misspelled position. Hey, we got Steve this time. All right.
So it works?
So
It worked for Steve.
you
Let's
need
see.
to search
Suzanne.
or
Should be Suzanne. Let's see what this one is. It's Steve again. Is that right? It's what?
I'm kind of stripped my paper out with no little thingies on it.
All right. Let's all congratulate.
hey, come on, that is
Does
And
anyone
this
have a
is
gold
why-
medal? Little money?
This is why you get loose leaf paper. Because
That's
all of the
kind hard.
pages don't have little fuzzy things.
Anyways, is this correct? Where
Sure.
Suzanne, where we print out Suzanne, or I'm sorry, print out the search of 111, it prints out Steve. Is that correct?
technically because it wrapped around.
Well, if we insert at 111 Suzanne, and then we go and search for 111, should we get back? What should we get back? Yeah, we should get back Suzanne, but instead we're getting back Steve. Why?
Because they collided.
Because they collided. Yes.
Her name, Nurse Victorious.
Because Suzanne wasn't placed in there.
Yeah.
Right. Why wasn't Suzanne placed there?
Because Steve was already there.
Yeah, Steve was already there, so
He
she had to
would've
take
been
the turn.
placed in 17.
In the next section, right, in 17, correct. So how do we fix that in our search?
Let's see.
So we get this position. What are we checking? If m hash table sub position dot, what do we have? Let's find out what we have. We have these three things: filled, key, and m value. And we're looking for key.
If the M key is equal to something.
The key
Okay.
will return.
False.
So if we have the key and we found it, we're good to go, right?
Yes.
All right.
What about else if to check so that Susan and Bob.
So if not, what do we do?
Else if?
We'll just continue because we're returning, so we don't have to involve the else ifs.
What if the L6 want to be involved?
But I'm being discriminatory. What do we check next?
If the key at the position at, say if it's found, check the key to see if it's the same thing. Same key of two objects, of two hashes.
So our search function already gets the hash of the key. So we already have that. And then we go to that position, and then if the node at that hash table's key equals to the key we're searching for, we return it. But if it doesn't, what do we need to do?
Add it to the array. Please keep searching.
Keep what?
Keep looking.
Keep looking. So how do we keep looking? What's the next item we look for?
The next item.
Yeah, the very next key.
Okay, so we would go position plus plus, and then we pretty much check this again, don't we?
Yes.
But what if that didn't work?
Then we have to plus plus again.
Right. Sounds like we need a loop.
Yeah.
Maybe we should do.
Don't be like one of those programmers that writes everything out.
What?
So you can
Don't
do
be
a
one of those
while.
programmers that write everything out. There are programmers I've seen recently that write everything out and don't use loops.
Well, you're having issues, so I'm trying to make this simple for you, Craig. Sorry, Craig.
It's too easy, I know. I know.
All right, so we should do while m sub n key does not equal key. We'll just increment the position, right?
Yes.
And then if the key at that position does equal that key, we'll return it. otherwise we'll return blank.
Blankety blank blank.
Because actually, what else could happen? What else do we need to check? There's actually one other thing we have to check.
Be sure not the end of the very last. You have to be sure that it checks for the last position. Yeah. Or no.
Or no.
Yeah, let's check for. Oh, it's good.
Yeah, because if it's not filled, then this doesn't make any sense, right?
Yeah. That was gonna be my next guess.
And we do need to make sure we wrap around with the position, so I'll paste that in there. And then if the key is there, and the m hash table sub position dot is filled, then we return it, otherwise we return blank. So what is this doing, guys? We're linear probing to find the next correct key. So it's going through, trying to find some position that matches the key until it finds either something that's not filled, and if it's not filled, and then once it's done finding that, it checks to make sure the key is there and it is filled. If so, return it. Otherwise, we just return nothing. Or actually, we should return null. Okay. Let's see if that fixes our problems. No, it made a lot of them though. Oh, I called it m is filled. I'm too used to Java. Actually, it's probably just m filled, isn't it? Yep.
Yep.
Almost there. M table, that's because it's m hash table. And line 63, looks like we forgot a semicolon. Yeah, we did. Boo. And then Suzanne. All right. Great. Hope you all are able to follow that. I feel like I did that really, really fast. Did I?
Comment your code.
I should not comment my code.
See?
Yeah, no one part of that doesn't come in either.
There you go. What was that?
Huh?
Huh?
Hmm?
All right.
Who said that?
Find the hash of the key. Find an open position. Fill in the position. Oh, that was kind of commented fairly well. Here, whoops. Get the hash of the key. Linear probe to find the correct key. Linear probe. Keep probing. Actually, I'll just say keep searching
Thank you.
until we either find the key or an empty space in the hash table. If found, return the string. Otherwise, null. All right, that looks good. Let's go ahead and run that part. No, that's good. And what are we doing here? Oh, let's do the full. We'll do the full on test. Let's see if this actually works. Oh, this might be terrible. Chain. No, let's not do that. No, we don't want to print that out. Oh, we don't care about that anymore. So we'll do the full search where we fill up the hash table and then make sure it gives us everything back correctly. And it did! Wow. That was pretty good. What are two things we have not implemented in this code? Remove.
Get. Oh, increase size.
The load factor.
Okay.
How do we compute the load factor?
That's a good question.
So int, I'll just call it size. Can I put equal to 0 here in C++? Does it allow me to do that? It does. How nice of it. Alright. 0. So when we insert and we succeed in inserting, we'll do size plus plus, right? How do we find out the load factor from here? Because we have size, or the number of elements inside the hash table. Yes, Caitlin. So with the size, how would we compute the load factor?
If it's.
Oh, I thought you were telling me something else.
No. No, stretching. If that is a certain percentage of the size that we have on the.
So we need to get a percentage. How do we calculate the percentage?
That number divided by the other number. Times 100.
Okay. Vector.
That's how you calculate it.
C++ get vector size. Make sure it is the size function. You can do it. It is just size. Ah, that's nice. So we can do m hash table.size. We'll make a double load factor equals that, so it converts it over. And then we'll have load factor divide equal the size we've computed. And then we'll go ahead and see that out right now. Load factor equals. You okay there?
Yeah, I'm fine.
What happened? Oh, the blinding light.
No.
It bugged him.
She bugged me with the pencil.
And I just realized we did that backwards. It's size divided by m hash table.size. Well, I'm tired. There we go. Start with the size, divide by the whole size. So this is a load factor.
Oh no.
Hmm.
It's the one. That's a no-no.
Yeah, no. Okay. So if load factor is greater than, what do we want our load factor to be?
0.8.
When we need to increase size. Uh-oh. Let's make a function. You know, function, conjunction, junction. What's your function? What?
Are you having fun singing?
Do you not sing?
Sometimes, but not that song.
That's not lovely.
Conjunction, junction, what's your function? Hooking up phrases. You don't remember this song?
Pretty awesome.
Schoolhouse Rock.
Yeah, there we go. How do we increase the size?
You have to duplicate the array.
We have to duplicate the array. All right, let's do that. What's the array?
Well, first you have to
So the array
make
looks...
an array that's double the size, and then you duplicate the array, and then you increase what your size is.
Okay, so we'll take it, we'll make a...
But isn't your one size a global variable?
Yeah, it's really just the number of elements. We'll double it.
Sure.
All right, now that we've doubled it, what do we need to do?
Then you copy everything over into it.
How do we do that?
Iterate.
We iterate. Okay, we iterate.
That was the right word for it.
Yes.
Just me.
Oh wait, we should do it the iterate. I don't want to iterate. Int I equals 0, I is less than m hash table dot size I plus plus. What do we do here? We hash each node into the new hash. I don't know why I called it new size. New hash table. Into the new hash table. And then we would replace the old hash table with the new one, right? Is that what you wanted to do? Good.
But there'll be a problem.
What is the problem?
In your face.
I see it in your face.
But I'm not going to cover this.
Wah wah.
Wah, 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 wah. All right, let's stop here and talk about your lab.
Oh no. What home is it?
Well, actually, hold on. We didn't talk about delete. So that's increased size. If we wanted to delete something, what would we do? Wow, our search and delete is really long. What would we do?
Don't we want to actually like not delete it? Just say, hey, it's deleted.
So we need to add something to our struct. What should that be?
It's deleted.
Deleted. All right, so we'll go down here.
Wait a second.
What?
Can you?
Oh no, you did fix the other one. Never mind.
Oh, we forgot to do this. Yes, Noah?
Never mind.
It does say that I was saying his name there.
So we insert it. mFilled is true, and mDeleted is false, actually. Which also means that down here we need to update this to be true. There we go, much better. So it is deleted. All values initially are deleted. So inside of insert, when we add it, we need to tell it it's now filled, but it's not deleted. So we're over here, delete the node with the key. So the first thing we need to do is find the position, right? Okay, now what do we do?
Deleted.
Equals true. Is that always correct?
If there's no value there.
Oh.
Well, also, what if there's a collision? What if you're trying to delete Suzanne, but she's not in the right place? So you got to do what?
Check. Check.
You need to probe. Search. Keep searching until we find a key or empty space in the hash table. So we want to copy, paste this up here. Well, the key doesn't equal each other, and they're filled. Find something. And then once you find it, then you want to delete it. Right? So I'm not going to test this code, and I know there is a error with it. We'll go ahead and get rid of the compiling error at least. There we go. But we're going to stop here because I'm not going to do the lab for you.